Welcome. I am Dr. Ruth Hummel on the JMP Academic team, and I'm the host of this webinar. We're joined by our special guest speakers, Dr. Bradley Jones and Dr. Douglas Montgomery today to discuss their new book, Design of Experiments, A Modern Approach. If you're a professor and you want to request an instructor evaluation copy or find other instructor materials for this book, you can visit the Wiley site, which is here on the slide. And now let's meet our special guest speakers. Dr. Bradley Jones is a Distinguished Research Fellow for JMP, where he's responsible for the development of new methods in design of experiments. And Dr. Douglas Montgomery is Regents Professor of Industrial Engineering and Statistics at Arizona State University. Both of our special guest speakers are experts in the field of design of experiments. Between them, they've authored hundreds of journal articles and other expert publications in the field of DOE. Today, they'll talk to us about their new book, Design of Experiments, A Modern Approach. Now, regrettably, I, your gracious and talented host, chopped off the first 2 minutes of our webinar recording, including a bit of the motivation for writing this book from Dr. Bradley Jones. So we join Dr. Montgomery as he shares why he believes this book is needed. Without further ado, here's Dr. Doug Montgomery.
Years at both the university level and to lots of different consulting clients and other organizations over the years, and my textbook, which is in its 10th edition, has about 65% of the market. So to discover that there's a 25% of the people that are not using the book was kind of disturbing, because I just cannot imagine teaching this course without having the kind of materials that you typically have in a textbook to support the students' learning. To me, it would be just an enormous amount of work, and I don't think my course would be a very good one. I think the problem is that many design books focus a lot on analysis. About half of the content of these books is analysis, and so a student gets the impression that there's only one appropriate design for any particular problem. Now, in our book, you will find some of the familiar orthogonal standard designs, but we approach the design problem as an optimization problem, and we use design optimality as our design selection or construction approach. And that distinguishes this book from anything else. Many times you will find a standard design here. It may be an orthogonal, fractional, factorial design. But it doesn't appear here because they're orthogonal or because they're a standard design, but they appear because they're optimal according to at least some criteria that we talk about in the book. And part of the real motivation here is standard designs, orthogonal designs, don't always exist for a given situation. And so what people sometimes do is they change the problem to fit the solution. And that's not always a very good approach in science and engineering and business. And so what we would like to emphasize is it's possible to create a design that is optimal in some sense for situations where standard designs don't work. And so this makes the optimal design approach much more practical and much more applicable to many of the kinds of problems that people encounter in practice.
Maybe we can mention a couple of the cases where that is a problem. For instance, sure. You know, if the sample size doesn't happen to be one of those magic numbers of
right.
Multiples of 4, or if the blocking, you have 3 runs per block or 5 runs per block, that might make it a little awkward.
Right.
Maybe certain factor combinations are impossible to run.
Right. So maybe even entire regions of the design space can't be used.
Right. So if you make the design space not be looking like a cube or a sphere, then that now becomes a hard problem from a textbook design point of view, because you could never in a textbook anticipate all the possibilities there.
That's right.
Okay.
So here, in our view, here are some of the really unique features of the book. We use the computer throughout. We virtually totally avoid hand calculations, except for just a couple of cases where we want to use the manual computing equations to get across the concept of techniques like the analysis of variance. So we rely on the computer for doing analysis. And of course, this is exactly consistent with modern practice. Nobody in the real world does analysis of variance calculations by hand. We use the computer for design construction. And we can also use the computer to compare different design alternatives because there's probably more than one design that works for your problem. And it would be nice to know up front what the properties of that are before you actually run the experiment. And then finally, we can use the computer to avoid printing tables of statistical reference distributions. You don't need these tables of t and chi-square and f and everything else in order to be able to actually do the statistical testing. Teachers will find that there's a lot of supporting material. We have a comprehensive set of PowerPoint slides for each chapter. And let me tell you, as somebody that's been teaching in the academic world for 50 years, I just don't have time to go out and create really good PowerPoint slides for a course. I just would not use a textbook unless there was a set of PowerPoint slides to accompany the book. Now, I would probably take those slides and modify them a little bit and put my own twist on it, but I want a starting point, and that's what we've given you. We've given you a comprehensive set of slides. And we also have jump data tables for the examples, and these tables have built-in scripts, so you can run them and you can reproduce the analysis that we get in the book pretty easily. If your university probably has a jump license, but if you don't know, you can find out by contacting the email address that you see on the screen here. And there's lots and lots of other additional JMP teaching tools that are available at the JMP website.
Yeah, so I think I remember the academic license people telling me that 190 out of the top 200 research universities in the United States do have copies of JMP, and that they can, and so students can download it from the university site. And we will, and you can work with the JMP academic team to make this an easy process for you and your students.
Right. Yeah, we have no trouble doing that here at ASU. Here is an outline of the book. This is essentially the chapter titles. And if you look through these chapter titles and you look at the flow, I think you would see that this is the outline of a pretty standard course on experimental design. This is exactly what I do in my course at ASU. My course here at ASU is a first-year graduate level course. It's what we call a 500 level course. And it's taken by first-year graduate students. It's also taken by some graduate students as well. And the only prerequisite for this class is a prior course in statistics. I always tell them that if they know how to calculate an average and standard deviation, and if they know how to interpret them, and they know what the normal distribution is, and it would be a bonus if they've heard of the t-test and the confidence interval, I tell them that they're ready to go because they're going to learn everything else that they need to know in the course. And I think we can say that about the book, can't we, Brad? That we cover all these topics at a beginning level that people can understand what's going on here without having to have a strong theoretical statistics background.
That's true. It would be helpful to know a little bit about matrix algebra, and if students don't know what a determinant is or how to take the inverse of a matrix, well, you don't have to take the inverse of a matrix. You let the computer do that for you. But those small things make it useful, and you might need to spend, if your students don't have that kind of prerequisite, you might need to spend 30 minutes getting them up to speed with that. Although we use the matrix notation quite a bit in the book because it's so much syntactically clearer, I think.
Yeah, it makes things simpler.
Indeed.
And I know my students who are mainly engineering and science students all have an adequate background in matrices. They get exposed to that in their required math sequence, and so it's usually not a problem. I think what we want to do is to now kind of walk through each chapter briefly to give you an idea about the content. Chapter 1 is an introduction to the general idea of experimental design. It gives you some historical perspective, and it also introduces you to a lot of the terminology that's going to be used later on in the book. We also have a recommended 7-step process for designing and conducting experiments, which I think is really quite important to success. All useful work is done in processes, and you need to have a well-organized and well-thought-out process for doing experiments, and that's exactly what we present you with in this chapter. We also give you a review of some basic stats topics that hopefully will be familiar to just about everybody.
Yeah, the thing that I really like about this chapter, which was almost completely written by Doug, is that it has, except for the very end of the chapter, which deals with the statistic stuff, but the beginning of the chapter says all the important practical considerations that you need to think about when you're starting and designing and running and analyzing an experiment. And I think it's really beautifully written.
Well, thank you. That's nice to know. Chapter 2 talks about what we call simple comparative experiments. That is a single factor, and the factor only has 2 levels, a low and a high. And many of you, of course, will recognize that the 2-sample t-test is a sort of a classic method for analyzing this kind of data. And we introduce this technique in that context. We also talk about the fact that the allocation of observations to each level of the factor is in a sense kind of an optimal design problem, and that the equal allocation problem or the equal allocation solution is really only optimal if the costs of running the experiment are the same at both the 2 levels, and or if the variance of the observations is the same at the 2 levels. And so we start to introduce the idea of optimality very, very early on here, even in this extremely simple situation.
Now, what you see on the graphic there is the probability of a type 2 error. That is, the type 2 error being thinking that there is no effect of changing from one level to the other when there really is one. And you can see that the relative importance of the various things that you could control, the error in the first sample, the error in the second sample, the sample size for each sample, the alpha level of the test, which you can see doesn't matter very much at all. But the most important thing is obviously the true difference between the 2 groups.
Chapter 3 extends what we did in Chapter 2. Once again, a single categorical variable, but now we have more than 2 levels. We have multiple levels. And the analysis of variance is the appropriate technique, or it is one of the appropriate techniques for analyzing this kind of data. And so we use this to give a general introduction to the analysis of variance, and some of the other techniques like multiple comparisons that are associated with that. And the graph that you see here is from an experiment in the book And we have a single categorical variable here, which is a mixing technique for a particular application. And we're using dot diagrams and box plots as a way to present the data graphic before you dive into any sort of analytical method.
So Chapter 4 changes it's still about one-factor experiments, but instead of the factors being categorical, in this case, the factor is continuous. And that means that it can vary, across a range of values. And so we have a motivating example in which the data are distributed rather evenly across the X space. And we discuss, fitting a line, fitting a quadratic equation, the effect on the estimates of the slope of the line of having the quadratic be the correct model. So there's a bias in the estimate of the intercept. And so we introduce the concept of aliasing, and then we also talk about optimality, because depending on the optimality criterion you use, you might get several different, the optimality criterion and the model that you choose, you would get several different possible designs. Doug, do you have anything to say about that?
No, that covers this really quite nicely. Thanks. Chapter 5 talks about factorial experiments, and we use the two-factor factorial as the motivating example here, and we show how the analysis of variance can be extended to the two-factor factorial case. We talk about different situations here. One situation is where both of the factors are categorical, and how the classic analysis of variance works in that situation. We also talk about the case where one of the factors is categorical and the other factor is numeric. And that leads to some different alternatives in terms of how you might analyze the data. And then finally, we look at the case where both of the factors are quantitative, they're numeric. And then we can fit response surfaces to the outcome of the experiment. And by the way, there's a much more extensive discussion of response surfaces later on in the book, but this is kind of a quick preview of some of that. We also talk about the importance of optimal design here, because there are many situations where optimal designs are required in the multi-factor case. For example, there can be constraints on the design region. Maybe the design region isn't a square or a cube or a hypercube. And there can also be situations where there are disallowed combinations. There may be a situation, for example, where one of the machines in your experiment can only be used by a subset of your operating personnel. So you have to sort out how to create a design where, let's say, one of your operators, in this case, we have 4 operators, Bob, Carol, Ted, and Alice, and Alice is not trained to use one of the machines. So you cannot run a complete factorial experiment where every test combination, every treatment combination is used in the design. So how do you deal with that? Well, we can treat that as an optimal design problem, and that's one of the scenarios that we talk about in this chapter.
Yeah, so it's not just optimality, it's optimality subject to a restriction, which
exactly
is interesting.
Yep, and that problem comes up a lot. Chapter 6 deals with blocking. Blocking is, of course, a technique that we use for dealing with nuisance variables. And most people are familiar with the classical randomized complete block design. In the randomized complete block design, every factor level appears in every block. And here's an example. We're looking at an extrusion process. There are 4 different pressures being used, And there are 6 different batches of resin, and the resin batches are the blocking factor. And each one of these blocks is large enough to hold every one of the treatments in the design. So this leads to the randomized complete block design. But there are many kinds of situations where this doesn't work. For example, your block size can be smaller than the number of treatments. And so now you have to have some sort of incomplete block design. And we show pretty nicely how these kinds of blocking problems can be solved pretty directly, pretty conveniently, using an optimal design approach.
Yeah, one of my demos at the end will deal with this very case.
Yes, and it's a nice example. Chapter 7 talks about a very special case of the factorial design, and this is where all the factors have 2 levels. These 2 to the k designs, as they're called, are wildly popular, very widely used in industry and in business scientific experiments because they're efficient. They're the most efficient way to study a group of k factors. And we show how these designs work. We include blocked versions of these designs. We have some examples that talk about different scenarios. And we also show that these are optimal designs. And this turns out to be a really important idea. 2 to the k designs are really basic building blocks. I always think of them as like DNA. You know, you can build a lot of really great stuff out of DNA. And these 2 to the k designs are powerful tools for doing that.
You can build a coronavirus out of DNA too.
Well, yeah, it's not always good.
Chapter 8.
Chapter 8 talks about the special case of factor screening. Many times the first experiment that you run in practice is a screening experiment. You've got a fairly large number of factors, and you're fairly sure that not all of them are important. So the purpose of this first experiment is to efficiently identify what we call the active factors. And 2-level designs are very useful for doing this, including fractional versions of these designs, because 2 to the k's suffer from the curse of dimensionality. You know, 2 to the 3 is 8, 2 to the 4 is 16, 2 to the 5 is 32. You can see what's going on here. 2 to the 10, by the way, is 1,024. And nobody's doing 1,024 experiments. In fact, not too many people are excited about doing 32 experiments the first time around. So when you have 4 to 5 or more factors, fractional versions make sense. And we go through the idea of standard 2 to the k minus p fractional factorial designs. We also talk about non-regular versions of these designs, which in many cases can be really efficient ways to do screening without having to do a lot of additional follow-up experimentation. And we also talk about a reasonably new development in this area called definitive screening designs, where factors can have more than 2 levels. And this is a very powerful idea, which we talk about in some detail in this chapter.
So the graph there is a correlation cell plot, which shows the little blocks in each cell show the correlation between pairs of effects. So the white cells are effects, pairs of effects that are not correlated with each other at all. And you can see that for this kind of design, main effects are completely uncorrelated with each other and with all the 2-factor interactions, which makes for an easier job of analysis.
Yes. Chapter 9, I'm sorry.
No, go ahead. Go ahead, Rod.
Chapter 9 talks about blocked designs where the blocks are random. And I almost always think about blocks as being random because if the blocks are fixed effects, then your inferences are only valid about the blocks that you used in the experiment. And a lot of times that just doesn't make any sense. For example, if your blocks are batches of raw material, you would want your inferences to be valid about all the batches of raw material that you're going to be using in that process. So analyzing these designs with the blocks considered to be a random effect is a very important idea, and we use this chapter as a way to introduce the REML method, the residual error maximum likelihood method, for treating random effects.
But we clearly also talk about the design construction problem.
Yes.
and how you set that up in matrix formulation. And it turns out using matrices, it's a much more elegant way to see what's going on in the
and easier to understand, much easier to understand. Chapter 10 talks about split plot designs, and we always, at least I always think of these designs in the context of hard to change versus easy to change factors. And when you have hard to change versus easy to change factors, complete randomization is really difficult. And so what split plot designs do is they take your hard to change factors and they put them in something called a whole plot where we don't change them as often. And then we take our easy to change factors and we put them in subplots or split plots within the whole plots. It turns out that these are random block designs, and your hard to change factors stay constant within the blocks. And the construction of these designs using an optimal design approach it's really the best way to create these split plot designs.
Yeah, so at the end of this chapter, we make recommendations for practical use of split plot designs, which I think might be very helpful. And I should also mention that going back to the screening design chapter, we introduced 3 or 4 different kinds of screening designs. But at the end of the chapter, we talk about under what circumstances you might prefer to use one type of design over another, and so have some sort of practical advice about those uses.
Brad, I think that's one of the things that we could say in general about this book is that we have really tried to put a lot of practical advice in the book in different places because I think that that's something that's really important for people to take a course in experimental design to carry away. I know in my own course that I teach here at ASU, I always tell the students that I'm not trying to make a statistician out of you. What I'm trying to do is I'm trying to turn you into an intelligent experimenter so that you understand what the choices are and that you can make intelligent choices when you actually have to design an experiment. And I think we've provided a lot of that kind of advice throughout the book.
Yeah, this book actually makes a lot of sense to be taught for engineering students. In particular, Doug teaches in the industrial engineering set of students at ASU, and for industrial applications, this book is really strong, I believe.
Yeah, I get students from all fields of engineering in my course. I get electricals, mechanicals, civils, material science people. I even get people from some of the other sciences. I get people from chemistry and physics and biology occasionally, not as often as I would like. But my campus class this semester has about 90 students in it, and they're spread across all fields of engineering. And one of the things that I do in my course is I force them to form teams and actually design and conduct an experiment. And the students get really excited about that because they say, well, gee, I didn't realize that we did that much experimentation in my field. And so I'm really trying to turn them into intelligent experimenters. And I think Brad and I have carried that flavor into this book in a pretty strong way.
I wouldn't want to say, though, that we think that if you're a statistics student, you shouldn't use this book. Or if you're teaching a course for primarily statistics students, certainly if at the junior or senior level, this would be completely appropriate for DOE class.
Yeah, many statistics departments in recent years have started to teach experimental design courses again. I think there was an era there where many experimental design courses in stats departments became sort of courses in clinical trials, and I think the pendulum has swung back, and I think this would be an entirely appropriate textbook for statistics students as well, because many times the statistician has to lead the effort in getting the experiment designed, and so having a good grounding in what is important in designing an experiment is really crucial. Okay, well, we got off track. We were talking about the outline of the book, and we've got a couple of chapters yet to go. This is chapter 11, and chapter 11 is all about response surface methods. And I always tell people that response surfaces is what you do after you've done screening. So once you've done screening, you know what's important, and then you can answer the next most important question, which is what are the best levels of these factors to use, the important factors. We want to maybe either maximize the yield or minimize the cost, or get certain quality characteristics of the output product on the target values that the customer wants. And we talk about the optimization techniques that are used to do that. We also present the classic response surface designs, like central composite designs. You'll learn all about those. We also talk about the use of optimal designs in this framework, because this is a place where very often you are unable to experiment over the entire design space. For instance, you may need to be experimenting in a region where if you try to use a classic design, the levels of some of your factors, the temperature and time, the combinations of temperature and time may be so extreme that you melt the tool, you melt the tool, or that you blow up the process. Yeah, a career-limiting move. So you need to, the optimal design approach is the right approach to go here. We also come back and talk again about definitive screening designs, because these turn out to be less expensive, less resource-intensive ways to examine a lot of factors, assuming that only a few of them are going to have any large effects on the response, and you'll still be able to fit a classic response surface model, which is usually a quadratic model.
So the final chapter is optimal design of experiments for models that are nonlinear in the parameters, and we include generalized linear models which have an element of nonlinearity in them. This is the graph here is showing the probability of success in a situation where you are using a binomial model with a link function. So we're just a short taste at the end of the book. You have anything you wanted to say too?
Well, these designs where you have binomial response data come up very, very often in practice. The classic examples, of course, are in things like clinical trials, where you treat patients with different dosage levels of a pharmaceutical product, And the response variable is they either got better or they didn't. It's either a 1 or a 0. But there are many, many, many situations where the outcome is either a success or a failure. And so understanding how to create designs for those kinds of scenarios is really important, because the best design for a normal theory response is a horrible design for binomial data. And so you really need to understand how to do this if you deal with this kind of response data.
So we've gotten through the book. At this point, there are 3 examples I'd like to show you that are examples that you would find in this book. So I'm going to switch. Well, I'll introduce the examples. The first one is a very standard example where you have 3 two-level factors, and you would be considering the 2 to the 3rd factorial design as an optimal design. But then you might consider the optimal replication of not the whole design, but 4 runs. The second example will be a blocking example showing the randomized complete block design is optimal, the balancing incomplete block design is optimal, and then something that's in between, which is neither not one of the standard designs, but which would have more power than the balancing complete block design. And then final example is an example where I go back to that infeasible design or infeasible restricted level combination with Bob, Carroll, Ted, and Alice, and the 4 machines, and show how that would work. So I'm going to escape out of my PowerPoint and move over to JMP here. So here's my first example. Here's a setup script in JMP for doing a 2 to the 3rd design. I have 3 continuous factors, and my ranges are here. Then I can choose a model. I could add the interactions, or I could add quadratic effects, or even higher order effects. And then you have to choose a number of runs, and the default number of runs is 8, which is going to give you the orthogonal design. Now, interestingly, in this case, you do get the 2-cube design, but you could just as well get 2 replicates of the 2 to the 3 minus 1, which is also optimal for the main effects. But in our case, we see that all the main effects are orthogonal to each other, orthogonal to the 2-factor interactions, and the 2-factor interactions are orthogonal to each other. The setup for doing the same problem, but with 4 replicated runs, is I'm going to put in the 2-factor interactions in the model now and ask for 4 replicated runs. And so the number of parameters that you're estimating here is 7, but in order to accommodate 4 replicates, you have to do at least 11 runs. And we're going to consider doing 12 runs. So this is the design that you would get. And you can see that the first 2 runs are replicates, the second pair of runs are replicates, the third pair of runs are replicates, and the fourth pair of runs are also replicates, and then you have 4 unique values. Looking at a data table for this problem and taking a quick look at the scatter plot matrix, you can see that we've replicated the green runs are the replicated runs, and they form a 2 to the 3 minus 1. This is a tetrahedron inscribed in the cube, and then the other 4 runs are the unique runs. I have to admit that, in fact, every one of the 8 choose 4 combinations of replicates for this problem gives you the same D efficiency. So this is just one of many possible D optimal designs in this case. But it's an interesting theoretical point, perhaps. Moving to the optimal blocking problem, here's the block design setup. I have pressure, which is being treated in this case as a categorical factor with 4 levels. Of course, you could also treat it as continuous, but you would get a different kind of design here. The blocking factor, when you define a blocking factor in JMP, you specify how many runs you can do maximally within a block. And so in this case, the number of runs per block is 4. And if you choose 12 runs, then the number of blocks, since there are 4 runs in each block, there'll be three blocks, each with 4 runs. But if you want the randomized complete block design, you need 24 runs. And so you would set that up like this. And then this is the orthogonal design and also the optimal design. You can see that all the effects are orthogonal to each other. And you can, looking at this, you can see that there are 6 blocks, each block of 4 has all 4 values of pressure. The balanced incomplete block design considers a case where I still have 4 different pressures that I'm looking at, but I only can, each resin batch can only accommodate 3 runs. And so you have fewer runs per block than you have levels of your categorical factor. And we can look at the relative standard deviations, errors of each of these estimates. And since the design is not completely orthogonal, because although the power effects are orthogonal to each other and the block effects are orthogonal to each other, the pressure effects are not orthogonal to the resin effects. Okay, but I wanted to show you one other thing, and that is this in-between case. So suppose instead of the randomized complete block design has 24 runs, the balanced incomplete block design has 12 runs. Suppose you were willing to do 18 runs. So now we have this in-between case, and you might choose to do this because the standard errors of the balanced incomplete block design are all 0.3, whereas the standard errors of these other estimates are substantially lower for every coefficient. So while you can't get such an elegant, look at the design as you do with the randomized complete block design or the balanced incomplete block design, this design is a compromise that gives you more power at a reduced cost. And the final example that I wanted to show from the book again is this example that has an infeasible factor combination. Here we have 4 operators and 4 machines. Ideally, you would like to have every operator run a part or 2 on every machine. But in this case, Alice isn't cleared to run machine 4. So if you were to do the 15-run design here, you would get, and I'll sort these left to right. Then what you get in the table is the first machine has all 4 operators, the second machine has all 4 operators, the third machine has all 4 operators, and the fourth machine is just leaving out the the last operator because they're not cleared. But you might ask yourself, okay, well, that's convenient, but what if I wanted to do 16 runs instead? What would happen? Well, now, again, I'm going to create the table. We can see that the last machine only has 3 runs, but the third machine has 5 runs, and that turns out to be more de-efficient than doing anything else. Also, it wouldn't matter whether it was the third machine or the second machine or the first machine that you replicated a run on. So these give you a flavor of both the kind of standard design that will pop up when you're doing optimal when you're doing things that naturally nicely conform to standard situations, but also shows the flexibility when things are are not quite as simple as the usual case that you see in a textbook. So those are my 3 examples. We have 10 minutes left to deal with any questions that might have come in during the webinar.
Okay, wonderful. Well, thank you guys so much for that description of what's in the book. There have been some questions coming in. I'll ask first, this question is to Doug. You earlier mentioned the sort of makeup of your classes and who's joining your classes, and we have a question about what types of other sciences, what representation you get from other sciences. Do you get geoscience majors? Do you get healthcare folks? What earth sciences? What's the makeup of some of the folks that you have in your courses?
I have had sort of all of those kinds of people in the course at one time or another. I would say that the majority of non-engineering students that I get are probably from chemistry or perhaps from a little bit more lately from geosciences, because one of our faculty members has a joint appointment there. I also get some people from the sustainability program from time to time, and you know, occasionally I'll get somebody from biology or somebody from physics, but mostly, you know, probably in any given class, about 90% of my students are from the classic engineering disciplines, and I get them all. Probably the biggest group I get are from bioengineering and from electrical engineering. I seem to get an awful lot of bioengineering students, and I serve on a lot of bioengineering PhD dissertation committees too. So I know for a fact that they are big users of the tools.
Yeah, but I happen to know that your class sizes are 200 or 300 sometimes. So
yeah,
you know, 10% of that is still a
lot.
Big number. Yeah, so you're getting non-engineers.
Yeah, this semester I only have about 90, but I have had classes of well over 200. It just depends on what's going on.
Okay, well, thank you for that. That was maybe your easiest question you're going to get. We're going to switch into some really tough ones now. So we've got a couple things in the direction of computer simulations or that sort of thing. So one question, just do you cover computer simulations in your book?
No, we don't, and that I think would be a really good thing to do as a homework question. When I'm doing computer simulations for research papers, you know, the computer simulation is often short, so you can afford to do full factorial designs, even heavily replicated full factorial designs. So that's maybe not quite as interesting as if you had a computer simulation model that was very expensive, then and you wanted more complex models, then you would have to be using a different piece of a different part of JMP than we're dealing with in this text.
Okay, great. And we have another very specific question. So assuming a scenario where you've got incidence of a particular disease or condition, by medical condition, and you've got a data set that kind of represents all the possible experiments you could run. So there's about 500 possible experiments with 12 different binary traits. So this questioner is asking, is there a recommendation, or does the book address how you would take from a space of 500 non-orthogonal options and make a selection of which runs to run?
The book does not deal with that problem, but the JMP designer does, in fact. Let me show you. So if you had a data table open with the 500 cases, then you would click this button here that says select covariate factors, and those would be the 12 or ever how many various things that you think might have to do with incidence of the disease, and then you would add these covariate factors there. And then the optimal design problem is to choose a subset of the 500 and you get to decide what size subset you're interested in. But if you could afford to do 100 of the 500, then you put 100 in the design, this number of runs, and it would find you the 100 runs that have the highest efficiency by whatever criterion you asked for. So that's a good problem. Certainly that could be shown in a class.
Okay, great. We've still got a couple more questions, and it seems like more coming in. Is there a limit to the number of variables with DSD?
No, there's no limit. Just to illustrate this, how about we have 1,000 variables?
Well, that seems excessive. Thank you. Okay, so our next question, do you recommend specific designs for experiments that rely on multivariate responses such as spectroscopy or mass spectrometry?
One of the things that's new in the latest version of JMP is functional data analysis and design for functional data. So if the output were a spectrum, then you could say that your response was functional, and then you would enter the number of things that you wanted to the number of let's say it was a spectrum, the number of wavelengths that you were going to discretize to. And instead of doing a separate model for each response, you would treat each response as a function and analyze it that way. So here's my 1,000-factor screening design with, well, there'll be about 2,000 runs. Yeah. So, and just that does seem extreme, but I do it just to illustrate the point that there's no limit.
Okay, great. One final question, because we've got 1 minute left. Does the book look at space filling designs?
It does not, and but again, that would be the kind of example that you might choose in a simulation experiment where you were thinking of a more complicated setting. But that is a part of the JMP design tools. It's right here and many types of designs are supported here. You can have sphere packing, Latin hypercube, uniform designs, and a rather new design that accommodates linear or constraints on the factor space. So,
all right, well, thank you.
That could be added, but it's not in the text.
Yeah, thank you so much for answering questions at the end and for sharing what's in the book. We got a lot of really nice positive comments also, a lot of people thanking you, Doug, for your series of design of experiment books that are so commonly used.
Thanks.
And I think a lot of people really excited about this new modern design of experiments book. If anyone has further questions that we didn't get a chance to answer, please send me an email. I've been posting my email in the chat. I'll post it there one more time. So let me know if you've got further questions, and I'll try to get answers back to you if I can. And I really want to thank you, Dr. Jones and Dr. Montgomery, again for writing this book, for sharing it with us, explaining what's in it, letting people know that this exists and that it's out there, and spending your time with us today to let us know what's in that book. So thank you so much.
We know that the next edition of the book has to have space filling designs.
Yeah. So thanks also to everyone who was on and gave us some feedback and some questions that hopefully will get implemented in the next version.
Thanks a lot.
Thank you so much. Okay.
Bye-bye.
Bye-bye.